Today we will review state variable methods of analysis of systems, which we did in 101. So, I will go through that quickly, the results which you have got, and go home and look out your 101 notes to get more details of that. What we said was, and Jade was the one who has initiated this way of looking at system through the state variable representation, although historically it is much earlier than that, but he was the first one to Jade and the Saur. And later on followed by Kalman. So, this what is the state variable representation? We said any state can be represented by a set of minimal variables whose knowledge at some time instant t0 if it is known, and then the input is known from that instant t0 to any time t, then everything about the system is known, provided you know the state variable, how they evolve. So, what we said is, if the state variables are represented by n dimensional vector space, then you are sitting at some state t0, and by giving a some inputs u t, you can move the state to some other state x t. This u t for t greater than t naught. So, given the initial state, you can apply a certain set of inputs to move the state to any desirable state, and a system which is defined by state variables x of t these are all vectors that have many components. Ut is the number of inputs that are provided to the system. It may not be one input, may be multiple number of inputs, and then you may also have multiple number of outputs y1, y2, y3, and all these constitute a output vector, and this constitute a input vector, and this constitute a state vector. So, the state vector graphically I am representing as a 2-dimensional state vector, but in general it is n-dimensional state vector. So, given this x of t0, by knowing this inputs for t greater than 0, we know how the trajectory moves from here to here, and once I know this x of t at any time t, y t is uniquely decided from the x of t. The equations we wrote was x dot t is equal to a x of t plus b of u t. I should put under the score showing that these are vectors, but I may not continue doing it. The x is a n by 1 vector, column vector, and A is n by n matrix, and B is a n by p matrix, where u t is the p number of inputs p by 1. Okay. This is p number of them. These are n number of state variables, and then y so the number of outputs may be some number, or So, this is r by 1 and this n by n by 1 and d again is n by p and p by 1. Okay. If it is a single input, single output system, one input here and one output here, but the number of states can be depended upon the minimal set that the system requires. This is the description for the system which is a LTI system, linear time invariant system.
Sir, if the Y matrix is R by 1,
Yes.
then there we are getting only N by 1 order.
Oh, then it should be R, right? Then this should also be R by P. So, R number of outputs now, this particular representation I have written down already for a linear time invariant systems, in the sense that this equation is a linear equation with respect to the input and the state, and then the time invariant because A and B are not functions of time, and it is linear because this is a linear representation, and time invariant because these are not dependent upon time. So, in general you can extend this idea to other kinds of systems like nonlinear systems, nonlinear time varying systems and so on and so forth, by appropriately modifying the equation, for example, as x dot t is equal to some f of x and t, where f is a nonlinear functional of x and t, and in which case it is a very general time varying nonlinear system. We will maybe sometime we will touch upon that, but let us not worry about that for the time being. The important thing that you need to know is that I do not care how this fellow has reached this point, from what past, given this x of t 0 and the inputs, I am able to find out what is the new state at any time t greater than t 0, as long as I know the inputs for t greater than t 0 and the initial state. So, important thing is knowing the initial state and knowing the inputs from the initial time to whatever time you want. Then I will be able to find out x of t. Once I know x of t, I can find any y of t by using this relationship. So, this is the state representation. The tricky part of this whole game is to find out what are those minimal set, right? How do I pick up the minimal set, or which is equivalent to saying what is the n here, what are the n number of variables which constitute a complete description of the system behavior. It is not an easy job to do that, but because what is the order of the system is a big issue by itself. But in the network theory, we showed that the energy storage elements happen to be the one which create the dynamics of the network, and hence the voltage across the capacitor and the current through the inductor happens to be the natural state variables for a network. But this need not be a network, it can be any system, mechanical system, hydraulic system, or any system for that matter, and to pick up what are those variables which constitute the states of the system is not an easy thing to do, but hopefully an equivalent ideas of network theory, like something which constitute energy storage elements like potential energy or kinetic energy, those elements which constitute those will be natural candidates for the state variables, right. But somehow you have to pick up this set of state variables. Then solution of this equation gives you x of t. I am running through because we have done this before. Solution of this first order differential equation, and this is sometimes known as a Riccati equation. Spelling is right or not, I don't know, but it's called Riccati equation. The solution of this first order differential equation it will give you x of t. Once x of t is known, I know everything about the network, because a network a system.